Hello everybody, in this lecture we will be solving 2017 USAJMO problem number 3. In an earlier video I claimed another problem to be number 3, but that problem actually was problem number 5. I added a highlighted note on that video that question is actually problem 5. But this one is problem number 3 actually, and here is a view of this problem. It's again a geometry problem. We're given an equilateral triangle ABC, as you can see on this picture here, and point P is on the circumcircle of the triangle ABC, and then we define three new points D, E, and F as described on the question, as you can see in the picture as well, D, E, F. And finally we need to show that the question is basically asking us to show that the area of DEF, triangle DEF, is twice the area of ABC, where these bracket, square, parentheses represent area. Okay, so this is a typical computational geometry problem because the question is asking for some area relationship. We will be using length relationships, and basically the tools that we can use when it comes to triangles. We might definitely use a law of sine, law of cosine formulas, and obviously we have a cyclic quadrilateral ABPC. As a result, we can also use Ptolemy and probably also some similar triangles as well. So similar triangles. So we'll try to use these formulas or concepts in order to derive length relationships. But first, let's try to find an alternative representation of this result. So showing this, I claim, will be equivalent to another result. But before I can do that, I want to do a little bit of angle chasing. Notice that on this picture, angle ABC is 60 degrees because we have an equilateral triangle. But this subtends arc AC. Arc AC is also subtended by angle DPC. So this portion is also 60 degrees. But in a similar way, angle ACB is 60 degrees. That angle subtends arc, minor arc BC, but that arc is also subtended by angle DPB. So this one is also 60 degrees. So and obviously finally, so these two add up to 120. So therefore angle BPF is also 60 degrees. So from this simple angle chasing, I have my first observation, namely that angle DPF, actually, DPF is equal to obviously 120 degrees, but that's also equal to, notice that this is also 60 degrees because BPE is collinear. So and this remaining portion is 120. So this is equal to FPE, which is equal to EPD, and they are all equal to 120 degrees. Now let's calculate the area of triangle DEF by splitting DEF into three pieces, namely DPF plus an area of FPE plus area of EPD. Now you need to recall that an alternative area formula was that, for instance, let's apply it on triangle DPF. It's 1/2 the length DP times FP times the angle between these two side lengths, which is the sine of angle 120. But in a similar way, we can represent FPE as 1/2 times FP times EP times the sine of angle FPE, but that's 120 degrees as we observed earlier, and finally plus 1/2, so area of EPD is simply 1/2 times EP times DP times the angle between these two sides are 120 degrees. So we can organize things here, so we can factor out the 1/2. We can factor out the sine 120, which is just √3/2. What's remaining is just dP times FP plus F EP times EP plus EP times DP. And now we need to show that this area is twice the area of triangle ABC, because ABC is an equilateral triangle. So we need to, so this one is what we need to show basically. So let me say that, show that this is twice the area of ABC. So 2 times the area of triangle ABC would be just BC squared, recall for an equilateral triangle, times √3 over 4. But then comparing these two results, I realized that the √3s will cancel out on both sides, and the 2's here and the 4 will cancel out. So basically, the question equivalently can be stated as follows. So equivalently show that this weird expression here, dp times fp plus fp times ep plus ep times dp, that's a p here, is simply equal to 2 bc squared. That's it. That's an equivalent representation. So all we need to do now is to show this result, and for that I will make use of the following thing. I would like to express all these lengths, and in fact there's 4 lengths here, namely dp, fp, ep, and finally bc. I claim I can represent all these 4 lengths in terms of simply BP and CP, and I will simply call BP as little b here, small case b, and CP as small case c. And in fact, in order to show this relationship, I will just represent the left hand side and the right hand side in terms of lowercase b and c, and see if this relationship really holds. So, as I said at the beginning of the question, this question is computational. There will be quite a few computations that we will be using, and we already started doing quite a few computations. So, going back to the picture, so we established that BP here, we called it as little b, and PC here is lowercase c. If you focus on triangle BPC, we can use law of cosine on triangle BPC. Law of cosine on triangle BPC would namely give me a BC squared as b squared plus c squared minus 2 times b times c cosine 120, right? So we would have BC squared is equal to little b squared plus little c squared minus 2 times little b little c cosine of the angle between the two, which is angle BPC. But angle BPC, as you can see here, obviously is 120 degrees, but cosine of 100, so this is 120 degrees, but cosine of 120 is equal to minus cosine of 60 degrees, which is minus 1/2, namely finally giving us b squared plus c squared plus the 1/2 and the 2 will cancel out, plus BC. So that's our BC square. So far we found this expression on the right hand side, so we can just multiply this by 2 and we would get the right hand side. All that's remaining now is to find DP, FP, and EP in terms of lowercase b and c as well, and so that's what I do next. So for that one, I will be employing Ptolemy on the cyclic quadrilateral ABPC. So let me write that down. So applying Ptolemy theorem, theorem on triangle ABPC. Remember that the product of the diagonals according to this theorem is equal to the diagonals, namely being AP and BC, so that better be equal to the product of opposite sides, the sum of the product of opposite sides, which is basically BP times AC, BP times AC plus CP times AB. And here, because our triangle is isosceles, all these BC, AC, and AB will cancel out. implying as a result that AP is simply equal to BP plus CP, but BP and CP are just lowercase b and c, so simply b lowercase b plus lowercase c. And next I will be doing some more angle chasing to establish that I claim, let me write that down, so I claim that triangle ACD, that's this triangle is similar to triangle APC. That's the first claim. I will make another claim next where I show two more similar triangles. So ACD is similar to, so ACD, you can clearly see it here. So this triangle here is, I claim, similar to APC. We can simply chase angles. Obviously ACD has a 60-degree angle here, and then you can associate this angle ACD with the angle APC of our second triangle, so because that one is also 60 degrees. And secondly, they share an angle A here, therefore their third angles must also be equal. As a result, you have the following length relationship. This implies that, for instance, AC to AP is equal to CD to PC, which is equal to AD to AC. And this would further imply that, making use of this and this and cross multiplying, we would get AC squared equals, we would simply get AC squared equals AP times AD. But recall that AC, the side length of our triangle, well, squared, is equal to this expression here. So I can just substitute BC here, and AP times AD, sorry for that, so this one is a D here, AP times AD. But AP, we already computed it as B plus C, so this thing is equal to B plus C times AD, finally implying that AD is equal to, and by the, well, yeah, let's first write that down. So that's equal to B squared plus BC plus C squared over B plus C here. So that's another length represented in terms of lowercase b and c. Still, I need these three, by the way. But then we can, noticing that AD is AD plus DP is equal to AP, which I know is equal to B plus C. Finally, I can get PD as a result. So PD, so this, therefore PD is simply equal to AP, the whole thing, minus, the whole thing, AP minus AD, so AP minus AD, but earlier we got AP as B plus C, minus AD, we got it recently as B squared plus BC plus C squared over B plus C. And if you find the common denominator here, we would get B squared plus 2BC plus C squared, and then when we subtract B squared and C squared, they will cancel out. So what we have on the numerator is finally BC, and in the denominator we have B plus C, and this is simply equal to PD. So we got the first result here, so perfect. So we got the first of these expressions. I still need to find FP and EP. Hopefully this will be easier due to the relative symmetry between the two expressions. So what I will do is I will establish some more similar triangles. Namely, I would like to claim that triangle FBP, let me actually use probably, let's use a blue color. So I claim that FBP, this one, this triangle here, is similar, as you can guess, to triangle ACP, the same thing actually, ACP. For that we need further angle chasing, but obviously you can see that these two angles are 60 degrees each. So what I'm claiming is BPF, angle BPF and angle APC are both 60 degrees. Furthermore, you can realize that angle ACP and angle ABP add up to 180 degrees because they are they are opposite angles on a cyclic quadrilateral. But then so it would further imply that that this angle, so ACP, is equal to 180 minus this angle ABP, but 180 minus ABP is simply FBP. So as a result, so let's write that down. So far we have that. Notice the following, or maybe I can directly make the claim first, and then I can explain why I believe that claim holds. So my second claim, claim 2, is that triangle FBP is similar to triangle ACP, and in order to establish that, I first observed that angle APC and BPF, because angle APC is equal to angle APC FPB. Do you agree? Angle FPB, right? FPB, and they are FPB, and they are both equal to 60 degrees. And furthermore, angle ACP is simply equal to 180 degrees minus angle ABP, but 180 minus ABP is simply equal to angle FBP, which is equal to angle FBP. So therefore, using angle similarity rule, we get that these two triangles are similar, which imply the following length relationships, such as FB to AC is equal to FP to AP, which is in turn equal to BP over CP. Now I can focus my attention on the last two, actually, this time. So, and all I need is an expression. Recall that I need an expression for FP. So therefore, this would imply that FP is simply equal to AP times BP over CP, and substituting here, recall that AP is B plus C, little b plus C, and BP was, we claimed at the beginning, here, BP is just little b here, lowercase b, lowercase b, and CP in a similar way is lowercase c, and we have the second result as well. So we are done with this one as well. Finally, what it remains is to find EP. In order to find EP, you can make the following claim, which you can prove it on your own, basically. That I guess triangle ECP is similar to triangle, I would like to say BP. And from here, and simply again using angle chasing, from here you will get that EP finally should basically come out as it will be basically a symmetric expression, like that. So that's EP. Remember that this one was FP, and we have the three distances, the three lengths, so namely DP, FP, and EP. Now we can substitute this into the left hand side and see if the equation holds. So we need DP times FP. And recall that so we need DP, so therefore DP times let me recall this result. So DP times FP, FP times EP, FP times EP plus EP times final one was DP. Sorry for that. DP. So let's plug these in. So we have DP, which was BC over B plus C, BC over B plus C times FP, which is B plus C times B over C. Remember there's a brackets here. Plus again FP, which is, I just wrote it, B over C times EP, which is C times B plus C over B. Finally plus, let me just squeeze it here, EP, which is C times B plus C over B times DP, which is the first result, which was BC over B plus C. Now when you compute all these, let's see what we get. So this B plus C here would cancel out, the C's would cancel out. I would just have a B square from the first term. From the second term, the b's cancel out here, the c's cancel out. I simply have b plus c squared. And finally, from the last term, the b's cancel, the b plus c's cancel. We have a c squared remaining, giving us 2 times b squared plus 2bc here, plus 2 times c squared, I believe. Or factoring out the 2, you get b squared plus bc plus c squared. But recall that b squared plus bc plus c squared is simply equal to bc squared. So therefore we have 2 times bc squared, and boom, that gives us the desired result. So we have just shown that this product sum, the left-hand side of the desired expression, is in fact equal to the right-hand side, and that solves the problem. Hope to see you guys in our next video.